Right. So number one, find critical numbers. So critical numbers just means set f prime equal to 0. If there's a numerator and denominator, then we set both equal to 0. But in this case, this is a polynomial. We're not going to have any denominator from the derivative, so just going to be your derivative numerator equal to 0. So let's try that. F prime. So I'll just work through the problem as you guys try it as well. Number two, find the absolute extrema on the interval from -2 to 3. This is an application of extreme value theorem. And we have to remember there's one condition with EVT. What is that? Function has to be what? Continuous. Yeah, continuous with brackets. Yeah. And we know we're going to be safe there. There's no vertical asymptote that's going to get in the way of our interval. So, and also it's a polynomial here. So we know our function is going to be continuous. So I don't think I put that on. Yeah, I did. So it needs to be continuous. And I'm looking for these conditions. Anything that requires conditions, I'm asking you to show that to our full credit. Now, extreme value theorem, what we're going to do is we're basically testing candidates to determine what the highest and lowest points are. So we have to make sure we consider endpoints, and we have to consider critical points. So critical points comes from what? How do we find critical points? Derivative, yeah, critical points from derivatives. So set the derivative equal to 0, solve for x. Are we going to, are all critical points valid? They have to be where? In between, yeah. And then once you find your critical points, and then once you confirm that they're valid, you're going to be plugging them into the original function and comparing y values. Is it possible that we don't find any valid critical points? Yes. And if we don't find any critical points, what do we do then? Are we still going to follow through with the theorem? We are, but we only have to test what? Just the endpoints. Yeah. So at the very least, I mean, once you can get past this condition, you'll be able to get an answer, max and min. It's just that if you don't find any critical points, it just reduces the number of candidates. You're always going to have at least 2 candidates, endpoints. You may or may not have additional critical points for candidates. All right, so let's try that. Find your derivative. Oh, and also when you find your absolute max and min, you're only going to give me what? Just give me, we want order pairs or just the, not the x, but the y. Yeah, so I just want the y values. I just want the maximum height or maximum y value or the minimum y value. Okay, I found 2 and -1. Are both of these valid candidates? Yes. Okay, use your calculator. Find your y values from the original function. I think on my key, I specified the x values, but just give me the y values. That's what I need from your answer. Mhm.
Is the reason to say it's absolute max, absolute min, is it just because it's on that interval?
It's exactly, yeah. So here we have a closed interval. So there's a definite highest y value and definite lowest y value. And it over the entire interval, this will be the lowest y value, that will be the highest y value. We don't say relative because relative would be if it's a polynomial and there are no bounds and you're just trying to find a hill and valley of the graph. That would be incorrect because if it's it might be a relative max, relative min, but that's not what we're asking for. We're asking for the absolute max and absolute min,
Alright, so EBT's for.
the highest and lowest points over the entire interval. It could be an endpoint, it could be at a relative max, but we don't care where it's coming from. We're just looking for the highest y value. Sign lines will be for first derivative test. We're never going to do sign lines for extreme value theorem. That's right. Those are just to find the hills, the peaks and valleys of your graph. Right. Yeah, so extreme value theorem is concerned about finding the highest and lowest points. First derivative test is just looking for the behavior of the graph. Where is the graph rising? Where's the graph falling? Where's there a hill? Where's there a valley? But first derivative test is not going to be committed to finding the highest or lowest points overall on the graph. Right, number 3, determine if Rolle's theorem applies. So Rolle's theorem is virtually the same thing as mean value theorem. So here's the formula for Rolle's theorem. Well, first off, what are the conditions for Rolle's theorem? Same as mean value theorem. Function needs to be what? And differentiable. And for us, right now, if you can get it past the first condition, it'll also pass the second condition. I mean, there are times when the graph will be connected, but not a smooth curve, but we'll deal with that later. But for now, if you can get it past the first condition, we can assume that it'll be smooth as well. So we need both conditions, continuous and differentiable. And then the formula, once we get past that condition, would be this here. You're going to find the slope between the two endpoints. You're going to find the derivative, and you'll set them equal to each other. All right. So slope doesn't require derivative. We're just going to find order pairs, find the slope. Then you find the derivative function, and then you set them equal to each other. And then you're looking for where they're going to match. The only thing with Rolle's theorem that is an additional requirement is that this needs to come out to be what? This needs to come out to a value of 0. If this doesn't give you a slope 0, then it's good for mean value theorem because we can guarantee a slope with the graph. But Rolle's theorem is specifically looking for slope 0. So if my endpoints do not produce a slope of 0, it doesn't quite fit under Rolle's theorem. But it's the same formula, same process, same condition. It just needs this portion to give you 0. All right, so let's consider the first condition, continuity. Is there anything that could disrupt continuity for this function? What do you notice about this function? Yeah, there's a what? Okay, where's the vertical asymptote located? Is that going to disrupt my interval? Yes. So will it pass the first condition? No. So we can say our function is not continuous. And therefore, we can't continue with this theorem. Rolle's theorem doesn't apply. For number 4, mean value theorem, virtually the same process as Rolle's theorem, same conditions, same formula. It's more flexible though. Rolle's mean value theorem doesn't need this piece to give you 0. It could be any slope. Could be slope 5, could be slope 8, could be slope -4. I mean, it could be slope 0 as well, but it doesn't have to be. Rolle's theorem has to be slope 0. Mean value theorem can take on other slope values. All right. Do you see any issues with this function? There's no denominator that's causing any issues. And also it's not 3 or 5 is not going to give us negative values. We're not going to have any issues. So we'll just practice writing out our conditions. So this is a requirement for anytime we're dealing with any theorems, we have to write our conditions. So remember, continuous is with brackets, differentiable is with parentheses. Okay, what's our next step? Yeah. Okay. Yeah, plug in the endpoints. Before we can find slope, we need to find order pairs. But once we find order pairs, we can do our algebra, find our slope, and then we can worry about the derivative. Okay, so my suggestion is don't find the derivative first. If you find the derivative first, you may get tempted to plug in the endpoints into the derivative, and we're not going to do that. So focus on your algebraic portion first. Let's find f of 3. And f of 5. Okay. Now we can take our order pairs, build our slope. That's your average rate of change. That's your slope. Change in y over change in x. Okay, we'll set this off to the side. We're not done yet, but we have one piece of the equation of the formula taken care of. Now let's focus on finding the what? Derivative, yep. To find the derivative, we have to go through what rule? Chain rule, yeah. Outside times inside derivative. Bring down the 1/2. Sorry, -1/2. I already have a negative in front. Keep the parentheses. Subtract 1 from the exponent. Multiply by the inside portion's derivative. Let's do some cleanup. Algebraic steps a little messy here. So if you bleed into number 5, it's okay because 5 won't take a whole lot of space. So I'm just going to set these equal to each other and cross multiply and try to find a way to solve for x. Yes.
Can you just explain the cleanup?
Explain the
cleanup.
Got it. So the -5 and -1/2, I'm just making it 5 in the numerator, 2 in the denominator. And I'm also pushing the parentheses to the denominator to resolve that negative exponent. And so that shares the space with the 2. All right, so I'm going to set these equal to each other. Going to just convert this to a square root. I think it makes it a little bit cleaner just to have the same notation. So cross multiply just to get rid of my denominator here. So this times this. All right, this looks messy here, but the thing is, if we just square both sides, then we can get rid of all the square roots, and then we can just, it'll be easier to combine all the terms together. So we can do that without having any issues because these are all being multiplied, so we can distribute the exponent through. It's not like as if we're adding a bunch of terms and having to FOIL it out. So all these terms are, we do see plus or minus in here, but this is inside the square root, so this is safe. I'm going to just square everything on both sides. Now, by this point, this should be a guaranteed solution. Is this, but just to confirm, are we safely inside the interval here? Yes, so we're basically looking for a slope of root 10 over 2 somewhere along this curve. And we found it at when x is 4.5, the graph is going to experience this exact slope, just like the slope that we found between the two endpoints. If you get more than one solution, just make sure that all of your solutions are inside the interval, and it needs to be between. So if it lands at the endpoint, it's not part of the interval. It's out. It's outside. It's not a solution. And if you don't get any solutions, that's an issue as well. You're guaranteed at least one, so we got to find at least one solution inside the interval. If you find your solutions and they're all outside the interval, go back, look at your work, because this should be a guarantee. All right, if the function polynomial, find the interval where the function is increasing and decreasing. We're going to go through what test here. This is f prime sign line, so we're going to apply the first derivative test. So you're going to find f prime, set f prime equal to 0, find your critical points, populate your sign line, find test points, and then look at your arrows, and then also justify your answer as well. So looking for all because statements, for you to include because statements when you write your increase decrease intervals. Number 6, same process as number 5. It's just that it's asking for relative max and relative min. But make sure you also include because statements. So everything that you pull from the sign line, you should always be able to create a because statement out of it. Even order pairs. But in this case, for number 6, is only asking for the x value. So I'm looking for you to practice writing out your because statements, your justification for number 6 and 7. All right, try 6. Does anybody still need the first page? Shouldn't that be negative? Yeah, sorry, max at -1. Everybody okay with the decode statements? Next one. This is test for concavity, so everything that you need will be from the second derivative function. So this one says find all points of inflection. So if I want to find an ordered pair, once you get your x value for POI, what would you do with that? How do you look for ordered pair if you have the x value? Original, yeah. So number 7, you do want to plug that x value into the original function to get your decimal y value. All right, any questions so far? Number 8, we have second derivative test. Thank you. Second derivative test is going to initially look like first derivative test. You're still going to find f prime. You're still going to find your critical points. But once you're here at your candidate's level, you're not going to create a sign line. You're going to plug these values into the second derivative function and look at the positive and negative signs of your concavity to decide whether these candidates are max or min. I will work through the steps with you for number 8. So with the second derivative test, you're going to start off like first derivative test. Find your critical points the same way from f prime. So these are the candidates we're going to test. These are the values that we're going to decide whether these are max and mins, but we're trying to do this without the sign line. So to do that, This is where the second derivative function is going to come into play. We're going to find f double prime. Power rule. And we'll do direct substitution with these candidates into f double prime.
There should be a side change. In hated table. Plus 20.
Oh, sorry, yes, it didn't factor that way, my bad. So for number 8, it should read minus 20x to begin with. Sorry, otherwise it wouldn't have factored. I changed it on the key, but not on your copy. So the original function should read 2x cubed minus x squared minus 20x minus 10. That's going to force that constant to be a negative, which will allow us to factor. Gives me negative 20 minus 2, which is negative 22. Again, this number is not going to matter to us. It's the fact that it's what? Negative. That means this is part of a what? Concave. Okay, negative is concave down. And if you visualize concave down, the only relative extrema you see there is a what?
Max.
Yeah. So we'll say relative max at x equals negative 5/3. Don't include the negative 22. Some students want to include that negative 22 as the max, but this is just a curvature value. If I want to find the order pair, I'll have to plug this back into the original function. But in this case, just indicating the x value is good enough. Let's test the other candidate. Give me a positive number. We don't really care about that number. It's the fact that it's positive. Positive means concave up. Concave up looks like this. We must be looking at a relative minimum.
Because.
No, you don't have to say because statements for second derivative tests. Your work will be your justification. Sketch a label graph of the function with the following characteristics. We haven't done this yet together as a class, so let's just walk through this. The idea is that if I can use these properties to create sign lines about slope and concavity, I'm going to take those shapes and try to create a graph out of it. So let me go through and talk about each of these statements here. F of 0 equals 0, f of 2 equals 0. These are just order pairs. These are the points that we can graph. Kind of help anchor a little bit. Okay, can we phrase this in a way that that we can visualize? F prime of x is greater than 0. What does that mean? Good. Positive slope. And where is the positive slope going to exist? To the good left of 1. Okay, left of x equals 1. So whenever they give you a value and say something is happening to the left or to the right of, that means it's a critical point. That means that number is going to go on your number line, your sign line, because there's a definite interval that is being created. So from that statement alone, we can populate a portion of the sign line. We can get this to show up, right? Positive slope to the left of 1. Interpreting that statement into a sign line. F prime of 1 does not exist. What does that mean? Good. Oh, there's two options. It could be a vertical asymptote or it could be a what? It could be a sharp turn. Right. But yeah, you're right. It can also be a hole. So if it says the slope doesn't exist, it could be because the point does exist, but the slope doesn't exist. Or it could mean the point doesn't even exist at all, and that's why the slope doesn't exist. So it's kind of a vague statement, but we can interpret however we want. It could be a vertical asymptote, it could be a sharp turn, it could be a hole. Okay, let's interpret the next statement. F prime of x is less than 0 if x is greater than 1. What does that mean? Slope is negative where?
Right.
To the right of 1. So negative slope to the right of 1. So if I can get the sign lines to show up, it can kind of bridge the gap between a statement into a picture. And we're going to translate this into a graph. It's a lot easier to translate this to a graph if we can see the arrows in front of us. Okay. F double prime of x is greater than 0 when x doesn't equal to 1. What is that? Can you phrase it that way? Good. Concave up everywhere except 1. Okay. And that the fact that x doesn't equal to 1 is also indicating to you that there's a critical point there, because they are indicating it's everywhere except at a point. And so there is a critical point that we can create. So at 1, we're going to create concave up on both sides of 1. So we're just going to try to create a graph that has a visual, that is visually consistent with our slope as well as our concavity. Let's start off with order pairs because they do provide us order pairs. So there's an order pair at 0, 0, and order pair at 2, 0. So let's treat this like it's a sharp turn. I'll also do the graph for vertical asymptote, but let's just say that it's a sharp turn. What would you expect at 1? There's a what here? Based off the arrows. Relative max. Okay. So there's a relative max somewhere at 1. I'm just going to highlight a point there. And I know my graph is going to increase and decrease. So I'm just doing I'm not doing the full graph. I'm going to lay out the path of the graph from my slope sign line, and I'll go back and retrace it with the curvature that I want. So, but I know that my graph is going to rise, hit some max at 1, and then decrease. Now, I want my graph to be showing concave up on both sides, but we're not going to do the full concave up. We're going to do a portion of the concave up because the graph is going to have to increase all the way through. We can't do a full U. So we'll just do a portion of that concave up, but still maintaining increasing because I know that the full shape is a U, but if we turn it into a U, then we're breaking the path that we've already created. We want the graph to be continually increasing. So then it's going to hit that peak. After that, it's still going to maintain concave up, but it's always going to be decreasing. So this is the rest of my graph there. I'm going to make that a sharp turn. So that sharp turn indicates the slope doesn't exist. So concave up increasing, concave up decreasing. So that's one option. The other option is where you force this point to be a vertical asymptote, which is also consistent with the fact that slope doesn't exist. Maybe the graph looks like this. This is also an option as well. Notice that whenever you're doing concave up and concave down, I think it's always good for us to sketch the path of the graph first and then match the curvature that we want. But we don't want to create a new path. Sometimes students want to create a new path because they say, oh, concave up, I want to bring that full U shape. But then you're creating a new path. Your path will already be created when you trace with the slope sign line, and you're just retracing that slope sign line with more information about the curve. Okay, let's start worksheet 2. We're not gonna have any homework this weekend, but we'll just work as much as we can in class. Okay, so let's start with page 5.
It's on Thursday.
Thursday, yeah, so we have some time. But I would like to get all of our review done by Monday so that we can start the new content on Tuesday, which is not going to be on the quiz, and then just save a little bit of time Tuesday to do final review. All right, find critical value numbers. What's our strategy here? Yep, first derivative, set equal to 0. If your first derivative has both a numerator and denominator, you're going to set both portions equal to 0 separately. Now, if you have split fractions, you may have to do common denominators before you can find your critical point. Let's get that square root to be ready for power rule. Anytime you have split fractions, split terms, we do need to merge them into the same fraction so that we can clearly see places to look for critical points. So I'm going to force the 1 below the 2x so I can consider my common denominator. All right, what's our common denominator here? Yeah, x to the 1/2. We need something large enough that both denominators can go into. That's going to be just x to the 1/2. Okay. Any adjustment with the first fraction? No, bring down the 8. The second fraction, though, we need to multiply by what?
X.
Yep.
Wouldn't that just be X? 3/2.
Mm-hmm. So here's my updated G prime. Set the top equal to 0, set the bottom equal to 0, and those will be your critical points. Raise both sides to the 2/3. This is going to come out to be some decimal value, so we'll leave it alone. To undo that 3/2, I'm just raising both sides to the 2/3 to undo and cancel that out, so that 2/3 gets transferred over. Number 2, extreme value theorem. What's our one condition? Continuous. Yeah. Are we safe with continuity? Yes. So extreme value theorem is the name of this theorem. Our strategy is find f prime, set f prime equal to 0. Consider your critical points. Make sure critical points are valid before you plug them and the endpoints into the original function. And then look at your y values. Highest y value is your max. Lowest y value is your min. And just give me the y values. Right, what do you notice about these critical points? -4 is not inside the interval. It's not part of our problem. We don't want to include that as our candidate. So we're just going to test how many numbers. There's 3. Oh. The 2 endpoints and the 1 critical point. Make sure you plug back into the original function because now you're looking for a physical location from your candidates. Just give me the y values. Okay, we'll pick up with number 3 on Monday. No homework over the weekend. Okay, go to your homeroom.
Wait, I think. Yeah.
Thank you. Have a good weekend.
We watch a documentary about.
Okay, homeroom, not your advisement. Homeroom.
Like, literally it's taken out, I literally, that was like. What? Yeah, but like 1 page is totally chat.
They're really interesting. You're really
Jack,